we use the sample median to test, and we know how to find the confidence intervals for sample median, right? So we know how to apply the assumptions, right? So all these things we talk about taking the parameter as sample median. But there are some cases where we are interested about the proportions in the population, right? There are so many cases that we are interested in the population proportion, where we take the population proportion as a parameter. So for an example, if you take if you are interested in knowing what proportion of votes will vote for a particular candidate in a given election, or if you are interested in all manufacturing firms are concerned about the proportion of defective items that they have in the given shipment, and let's say a market analyst may wish to know the proportion of families in a certain area who have central air conditioning. So likewise, sometimes we are interested about the population proportions. In those cases, we cannot take the parameter as the median, so you have to take the parameter as the population proportion. In such cases, in order to do a hypothesis testing on population proportion, when you have a small sample, we use this binomial test, right? So when we use this binomial test as the sign test and as the Wilcoxon test, we have some assumptions to satisfy, right? So one assumption is the data consists of a sample of outcomes of n repetitions of some process. Each outcome should consist of either a success or a failure. The proportion of the sample having a characteristic of interest is, we take it as p hat. An estimate of the population proportion, P is an estimate, where S is the number of successes, the total number of sampling units with a particular characteristic of interest. That is, if you want to apply the binomial test, when you take your small sample, you should see n number of repeatable events in your process, right? So if, like for an example, if you have 10 observations in your small samples, those 10 observations should come from 10 repeatable process, right? So when you take those 10 observations, right, you should be able to divide each observation as a success or a failure if you want to apply this binomial test. And what we do is we look at the sample and we count the number of successes you have in the sample, and we divide it by the sample size. For an example, if you have 10 observations, and among 10 observations, if you have 3 successes, we divide 3 by 10, so that is 0.3. So we take this 0.3 as a estimator for the population proportion, right? And all these n trials, if the sample size is 10, these 10 trials should be independent, right? And then the probability of a success, it should be a constant, right? It should remain as a constant throughout all the trials. It cannot be changed. So actually these are all the assumptions of the binomial distribution. So we need to satisfy all these assumptions regarding your small samples if we want to apply the binomial test to do a hypothesis on population proportion. So as we discussed for the median, when it comes to the binomial test also, you can conduct one-sided test as well as two-sided test, right? So first we'll discuss about the one-sided test. So if you take the one-sided test, here there's a small mistake, I'll make it correct. It should be the alternative hypothesis H1. So when you take the alternative hypothesis, let's say if you take the population proportion as P, And let's say you want to test whether the population proportion is less than a given value. So I'll take the given value as P naught. So you can write the one-sided test hypothesis H1 as P less than P naught. So as we discussed in the median, in the test that we use for median, when it comes to the null hypothesis, you can write it as P equal P naught, or else you can write this one as P greater than or equal P naught. Here, if you want, you can write P greater than or equal P naught, right? Whatever the way you like. If you just keep it as P equal P naught, that would be fine, right? So now, after reading your question, the first thing is you have to identify whether it's a one-sided test or a two-sided test, and then you should be able to write down your hypothesis. So after writing the hypothesis, then you need to know how to calculate your test statistics. So in this case, when you calculate the test statistic, right, the test statistic is the number of successes. So I will just write it here. So then after writing down this the hypothesis, you have to write the test statistic. So in this case, the test statistic, that is denoted by S, where S is the number of successes in a sample. So S is the number of successes in the sample. So that you have to calculate. So that would be your test statistic. So after calculating the test statistic, we are going to calculate the p-value for your sample, right? So the p-value, when you calculate the p-value, so p-value here we calculate p-value is equal to the probability where the test statistic is less than or equal to the observed value of test statistic. So I'll denote it by S naught, observed value of test statistic, right? Given that the sample size is n, right? Given that the sample size is n, and the p naught is the value that value that we use to test the population proportion, right? So we know since we at the beginning, in order to apply the binomial test, we need to check whether all the assumptions of the binomial test is satisfied, binomial distribution is satisfied. So because of that reason, for our test statistic, it has a binomial distribution. So since it's having a binomial distribution, to calculate the p-value, we use the binomial distribution. So we just observe the number of successes, that is our test statistic. So based on that, we calculate this p-value. So then after calculating the p-value, you can take your decision, right? So if this p-value is less than alpha, we can reject H naught, right? We reject H naught if the p-value is less than alpha. So that is what you have to do when it comes to the one-sided test. I'll just copy this so it would be easy when we illustrate the one-sided test. The next one. So if you are interested in a one-sided test, but here if your alternative hypothesis, that is H1 is P greater than P naught, in this case also you can write down the null hypothesis as P equal P naught, or else you can write it as P less than or equal P naught. That is as you wish. So in this case also, we need to, first thing is like this, we have to write down the hypothesis, then we have to write down the test statistics. So it would be the same. The test statistic is the number of successes in our sample, and then we need to calculate the p-value, right? So when we calculate the p-value, in this case here it should be the probability where the test statistic is greater than the observed value of test statistic, given that sample size is n and p naught is the value. This is the p naught one, right? The value that we are testing for the population proportion. So these given these values, we need to find the p-value. So as in the previous case, when you take the decision is if the p-value is less than alpha, we can reject h naught, right? So when you take this one, actually when you take this one, when the h naught is when h naught is true, right, we know we can observe a binomial distribution when h naught is true. So that's why we are using this binomial distribution in order to find out the p-value. So the next one is, how are you going to do the two-sided test? Right, so in the two-sided test, we know we have h naught as p equal p naught and h1 as p not equal p naught. So in that case also, the test statistic would be the same, that is the number of successes you have, right? So in this if you look at the previous cases, that is if you look at the one-sided tests, now if you look at this one, if you look at the first one-sided test that we discussed, right, in this one, so actually if we want to reject h naught when we observe the sample, if you have small number of successes, we would get with the decision to reject h naught, right, when h naught is true, because here we can see when the null hypothesis is true, the proportion is less than the given value. So because of that, when you have sufficiently small values of that is, if you have a small number of successes, we tend to reject h naught, right? And in the next one-sided test, the second one that we discussed, where your alternative is greater than p naught, in that case, if you have large value for your test statistic, that is if you have so many successes in your sample, so in that case there is a tendency to reject h naught. So when it comes to the two-sided test, what would happen, right? So in that case, we cannot see sometimes for sufficiently large values or sometimes for sufficiently small values of s, we reject h naught. So in this case, let's see, when it comes to a two-sided test, so the first thing is, when it comes to two-sided test, as we discussed, first you have to write down the test statistic. So the test statistic we know how to write down, and then that is the number of successes in the sample. So you have to find out the test statistic. So the next thing is how we are going to calculate the p-value. So in this case, when you calculate the p-value, what you have to do is, first you have to find the probability where the test statistic is greater than s naught, given that your sample size is n and the value that we are testing is p naught. So you have to multiply this by 2, right? Here you have to apply this formula. You have to apply this formula if S divided by N, that is the estimator of the population proportion that I will write this as not S, since this is I will write it as S, or else you can just replace that by S naught. So this is the estimator of the population proportion. So how you are going to calculate this? this is the test statistic S. You count the number of successes in your sample and divide it by sample size. So we are going to calculate the p-value using this formula when if this S divided by N, that is the p hat value, actually the estimate, if this is greater than p naught, then we are going to use this formula, right? If the estimate value is estimated value for the population proportion is greater than the given value that we are using to test, we are going to find the p-value using this formula, right? Or in the other case, right? Or what we do, or when you or if this estimate value is less than p naught, what we are going to do is how we are going to calculate the p value, that is the probability where S is less than or equal the observed value of the test statistic given that sample size is n and the value that we are testing is p naught. So using these two methods, we are going to find out the p-value. So if the p-value is less than alpha, just as before, we are going to reject H naught. So this is how we are going to use the binomial test, right? So let's just see an example. Alright, so if you look at this first example, it says in a survey of injection drug users in a large city found that 2 out of 12 were HIV positive. Right, so what has happened in a large city? They have conducted a survey, right? So they have found that 2 out of 12 were HIV positive. So we wish to know if we can conclude at 10% level of significance that fewer than 40% of the injection drug users in the sampled population are HIV positive. So there are drug users, the injection drug users. So using a survey, they have collected information from 12 injection drug users. So out of those 12, 2 were HIV positive ones. So what we want to do is we want to test whether 40% of the population from this injection drug users are less than 40% of this injection drug users are HIV positive. So that is what we have to test here. So the first thing is, now after reading the question, the first thing is we have to write down the hypothesis. So in this case, I'll take, that is P is the population, P is the that is the proportion of the drug users who are HIV positive, right? Portion of drug users who are HIV positive, that we can take as the one that we are going, that's the one that we are going to test actually. So I take that parameter as P. So now we can write down the hypothesis first. So what is the hypothesis? In this case, we can write down, since our claim is to check whether fewer than 40% of them are HIV positive, you have to take the claim as H1, your alternative hypothesis. So that is, we can take, right, we can take P less than 0.4 as our alternative hypothesis. So when you write the null hypothesis H naught, you can take it as P greater than or equal 0.4, or you can just write P equal 0.4, right? Both ways would be fine, but it's convenient for you, you can write it as it is. So this is the first step. You read the question, identify that here you have the proportion. We are interested about the proportion, not a median. So we are going to apply the binomial test. Alright, so first we write down the hypothesis. Now the second one is, now we have to calculate. Now they have given the alpha value, so the 10% level of significance we have to do the test, so that is the alpha value, we have to take it as 0.1, right? So that one is also there, and here we have the sample size. I will just note it down. The sample size is equal to 12. That also we can note down, right? So we know when you take these people, or when you take a unit from out of these 12 observations, that one would be HIV positive or not. So that would be a success or a failure, right? And these people are independent from each other. So we can see all the characteristics of the binomial distribution. So that is when H naught is true. If you take S as a success, or if S as the number of HIV positive ones, so that is S is having a binomial distribution, right? S is having a binomial distribution. Sample size is 12, and here the probability of a success we can take as 0.4, because that's what we are testing, right? So that is also there. Now in this case, the S naught value is the one that we are testing, right? The S naught value is the one that we are testing. That is the observed value of our test statistics. So what is the S naught value here? So when you take the sample out of 12, we have 2 HIV positive ones. So that is, we have only 2 successes. So observed value of the sample is equal to 2. So now we can, so this is a one-sided test. We know the hypothesis, we know the test statistics. So the next thing is how to calculate the p-value. So I have given you the formulas how to calculate the p-value. So in this case, we know p-value is equal to the probability where our test statistic is less than or equal to S naught value. So here the S naught value is equal to 2. Right, given that the sample size is 12 and p naught value is 0.4, that is what we are testing. So now from the binomial table we need to find this out. So I'll just have a look on the binomial table. Now our sample size is 12, so I'm going to quickly see, now this is where we are. So our sample size is 12 in the binomial table, right? So this is our sample size, and then what we have to do is, so we have 2 number of successes. So here you have to read 2 from this one, and if you take the proportion is equal to 0.4. So at the intersection point we can read out, right, here you have 0.4, here you have to read 2 from this side. So at the intersection point you can read the probability, because this is the cumulative binomial distribution. Right, so you can see at the intersection point you have this probability, that is 0.0834. So that is the probability. So you can straight away, since this is a cumulative and since we are interested about the less than probability, you can take the value from the binomial table straight away, right? So this is the p-value. So p-value we can find it like this. Now what is the decision? So what is the decision that you have to take? If the p-value is less than alpha, we can reject the H naught. So here alpha is 0.1 and the p-value is 0.0834. So the p-value is less than alpha, right? So we can reject H naught. So what is our decision? We reject H naught under 10% level of significance. Right? So that is our decision. So if you reject H node, that is our claim is true. So what is our conclusion? Then we can write down our conclusion. What is our conclusion? So our conclusion is fewer than 40% of the injection drug users in the sampled population are HIV positive, because that was our claim. So the claim is correct. So we can conclude that fewer than 40% of the drug users in the sample population are HIV positive. So it is very easy. So just like this, you can easily apply the binomial test when you are checking for a population proportion, right? So there's another example where you can try it at home. Right? So as in the Wilcoxon test and the sign test, when it comes to the binomial test also, you can use the large sample approximation. Right? So when you're using the large sample approximation, what you have to do is, here we have to take the mean value as NP naught and the variance NP naught into 1 minus P naught, because we know these are the mean and the variance of the binomial distribution. So our test statistic, in order to convert it into a standard normal distribution, we have to subtract the mean value and divide it by the standard deviation by taking the square root of that. So in that case, we can apply the large sample approximation. So when are you going to apply the large sample approximation? You have to take, right, if you want to apply the large sample approximation, when are you going to apply the large sample approximation? That is, under two conditions you can apply the large sample approximation. One condition is you can just check whether NP naught value, right, that is the sample size, you have to multiply by the given value that we are going to test, right, the given proportion value. If it is greater than 5 and n into 1 minus P naught value is greater than 5, then we can apply the large sample approximation. Right? So let's discuss this using this example so that it would be very clear for you all, I guess. Right, let's see example 3. It says a commonly prescribed drug for relieving nerves tension is believed to be only 60% effective. Experimental results with a new drug administered to a random sample of 100 adults who were suffering from nerves tension show that 70 received relief. Is this sufficient evidence to conclude that the new drug is superior to the one commonly prescribed? What has happened? For the people who are having nerves tension, they have introduced a new drug, right? But they say in the new drug only 60% is effective. So what they have done is they have taken a sample of 100 adults, right, who were suffering from this nerves tension, and they have given this new drug, and among those 100 adults, 70 of them have received relief. So according to this information, we have to conclude whether the new drug is superior, whether the new drug is superior to the one that they have already been used. So that is what we have to do. So what is the first step? The first step is we have to write down the hypothesis. Now what is the hypothesis? Now there are these people, the patients who are having this nerves tension. So from their drug, from the prescribed drug, only 60% is effective, right? So, and then they are going to introduce a new drug. after doing some experiment. So if the new drug is superior than the previous one, from the previous one 60% is effective. So the effective percentage should be higher for the new drug, right? So if you take the proportion in this case, right? So we have to first write down the claim when we are writing the hypothesis. So if I take the proportion, the percentage of the people who get relief using this drug, it should be greater than 0.6 if this is a superior one than the commonly prescribed one, right? Because in the common one already 60% of them get relief. So if the new drug is a better one, it should be a better one, it should give better solutions, right? So because of that, the percentage that would get a relief should be higher than the commonly one, right? So if from the common one 60% get a relief, so if this is a superior than the commonly one, so the percentage should be higher. So the proportion should be greater than 0.6. So that would be the claim. So I take it as H1. So now I can write my null hypothesis H naught, that is, you can write it as P equal, you can just write it as P equal 0.6, right? Or else you can write it as P less than or equal 0.6, whatever convenient for you, right? Since I wrote with the equal sign in the previous one, I just wrote it in like this for this example. Alright, so now after writing the hypothesis, now you can see it's not a small sample, you have 100 observations, right? So if you just take NP naught, if you take NP naught multiplication, right? So if you that is sample size is 100, P naught is 0.6, the value that we are testing. So this is equal to 60. And then if you take N into 1 minus P naught, right? If you just check this one, N is 100, 1 minus P naught is 0.6. That is again equal to 40. So you can see NP naught and N into 1 minus P naught both are greater than 5. So this condition is satisfied, that is we can apply the large sample approximation. Right, so they have given the alpha value as 0.05, so we just take it here. The alpha value is equal to 0.05, so we are going to calculate the test statistic using the standard normal formula. So in this case, S is the test statistic, that is the number of successes in your sample. So we have 100 patients, out of them 70 has received a relief. Right, so that is we have 70 successes in the new sample, minus N is 100, P naught is the value that we are testing, that is 0.6. Right, so this one you have to divide by the square root value of N is equal to 100, P naught is equal to 0.6, 1 minus P naught is 0.4. Right, so if you substitute all these values and see, you can get the test statistic value. So in this case, it would be 2.012. Right, so now we know if this is having a standard normal distribution, this is having a standard normal distribution, we know the cutoff marks, right? So if this is having a standard normal distribution, since we are testing for the proportion greater than 0.6, we know our critical value is falling in our right hand side, right? So which is equal to 1.64, close to 1.64. Right, and since we can see our test statistic is greater than 1.64, so that is our test statistic is falling in the critical region. So that is we can reject H naught. So I'm not going to discuss how to find this critical value using the standard normal table, right? That you have already discussed in your first 2 years, right? So by now you should be able to find out those critical values. So if this test statistic is inside the critical region, we reject. So that is, if it should be inside the critical region, it should be greater than 1.64. So if our critical value is a negative one, let's say it's minus 1.64. So if your test statistic is inside the critical region, your test statistic should be less than this critical value. Since this is a positive number, so here you need to have your test statistic greater than this critical value in order to get it inside your critical region. So in our case, this is inside our critical region, so we can reject H naught, right? So that is, we can conclude that if we reject H naught, that is the proportion is higher than 0.6. So our conclusion is the new drug is superior to the one commonly prescribed. So that also you have to write in the exam. What is your conclusion, right? So like this, you can apply the large sample approximation also using the binomial test, right? And also when we use the binomial test, right, we can find the confidence interval for the population proportion using this formula. Right, you can see the population proportion. You have p hat. P hat is the estimator that we take using our sample. That is, you have to check how many successes in the sample and divide it by the sample size, right? And then Z1 minus alpha by 2, that is coming from the standard normal table. N is the sample size. So using this formula, we can easily calculate a confidence interval for P, right? So if you just quickly have a look at this example, it says in a certain university the proportion of students who have diabetes is P, right? Have diabetes is P. Of the 500 students selected at random from the university, 6 had diabetes. Find a point estimate of P. Construct a 90% confidence interval for P. Now you can see, first they have taken 500 students from a university, and out of 500, there are 6 students who are having diabetes. So you need to find out, if you take the P as the proportion of the students who are having diabetes, first thing is they are asking you to find out a point estimate for P. So that is very easy. The estimate is, if you look at the sample, there are only 6 students who are having diabetes, and in order to convert this into a proportion, this is out of 500. So you have to divide 6 by 500. So that would be a point estimate for P. You can denote this by P hat if you want. And then you have to calculate a confidence interval. So what you have to do, you can just take this formula, right? So this, so what we calculated here is the P hat. Right, you can use these notations, and now we know the P hat value, so you can just substitute the P hat value to the formula, so you have no problem there. And since we are going to calculate a 90% confidence interval, right, we're going to find out 90% confidence interval. So that is when you take the alpha value, just that is when you take the alpha value, alpha should be equal to 0.1. So if alpha is equal to 0.1, since it's a confidence interval, we are interested about the 2 edges. So we need to find alpha divided by 2 value, which is equal to 0.05. Right, so because of this, if alpha is this. So then what you have to do is, then we have to find out the cutoff points, right? So that is one cutoff point is from the standard normal table. You have to find out that is Z 0.95 value, right? Is it 0.95 value? We know from the standard normal table. Is it 0.95 value means you need to find out the number where you have when you take the area of the standard normal distribution, which is from the reading point you have 0.95 of area which is less than or equal to that given reading point, right? So that is what we meant by that. Right, is at 0.95. So actually this is at 0.95 value, that is a commonly used value in statistics. So as statistics students, we all know what is that value. So that is 1.64, close to 1.64, right? So you can substitute for the Z value here in the formula. For the Z, 1 minus alpha divided by 2. Versus this one you have minus 1.64. For here you have plus 1.64. So N is the sample size, that is 500. P hat also we calculated. So everything is known. So you have to just substitute and find out the confidence interval. You just simplify it and see. So you should get an answer which is close to 0.04 and 0.02. The confidence interval you can give as 0.004, 0.02. So actually when you use the binomial test, you can see here I have used the standard normal table to find out the confidence interval. That is, if you're using the binomial test, you should be able to use the large sample approximation if you want to find the confidence interval. In other cases, if you have a small sample there, we are unable to find a confidence interval using the binomial test. That is using for the population proportion. If you have small sample, it's hard to find a confidence interval. We cannot actually. But if you have a large sample, then we can find out a confidence interval. So here we can just conclude the proportion of the diabetes are in between 0.004 and 0.02 with 90% confidence, right? Okay, so I hope that you're clear with the binomial test and how to use the assumptions, how to use the test, and also how to use the large sample approximation, and also how to use the how to find out the confidence interval. So we'll discuss about more testing procedures from our next session. So till then, thank you so much.